Question 3 is talking about carbon monoxide reacting with chlorine to form the phosgene gas, according to this reaction below. So carbon monoxide, chlorine, phosgene. Equal amounts of carbon monoxide and chlorine are added to 2 empty vessels and allowed to react at 2 different temperatures. The graph below shows the amount of phosgene produced. So therefore this graph here is showing the production of phosgene over time. And you can see that we have our 2 different temperatures, T1 and T2. Circle on the graph, circle here, which temperature is greater and explain your response. So what do I know about temperature? As I increase temperature, I'll increase rate of reaction. So I'll increase the rate, and I'll also favour the endothermic reaction according to Le Chatelier's principle. So therefore, what's going to be happening here? Here I can see that with T1, it has a lower slope, so therefore it's being produced at a lower rate here, whereas at T2 my rate of reaction is it's getting produced faster. It doesn't produce as much, but it is still getting produced faster. So that's how I can tell between these 2 temperatures. So I'm going to say temperature 2 is my higher rate of reaction, so therefore it must be the temperature. So therefore with this, explain my response. T2 has a higher initial rate of reaction producing producing phosgene, COCl2 gas. This is because the slope on the graph is steeper. Alrighty, steeper. So therefore, we have an understanding of temperature. As I said, temperature increases the rate of reaction, so therefore we should see an increase in phosgene at a quicker rate. Also, it should favour the endothermic reaction. I don't know about that yet because we don't know what the delta H is here. But that's the answer to part A. Is this reaction exothermic or endothermic, and explain your response? Okay, so this is where I need to understand the Le Chatelier's principle aspect of it. Now, my higher temperature, I would have favoured my endothermic reaction. That's produced a lower amount of phosgene, which means my backwards reaction would have been favoured. If I look at it, at T2, I have a lower temperature, so therefore, but I've produced more phosgene. So that suggests that my forwards reaction is going to be exothermic. Now let me write that down nicely for you, and let's have a look at it. So what this is saying is a lower temperature favours the forwards reaction, because you can see I've got more phosgene produced at my lower temperature. So therefore the forwards reaction must be exothermic, because at a lower temperature, Le Chatelier says I'm going to try and oppose that by warming it up using an exothermic reaction. So therefore my forwards reaction is exothermic. So I'm going to go exothermic. Now let's explain that. At my lower temperature, I produce more phosgene, COCl2. Therefore, lower temperature, lower temperature will favour the exothermic reaction. Thus, the forwards reaction producing COCl2 must be exothermic. And therefore, we have our response. Okay, so therefore, at a lower temperature, I produce more COCl2 because that's just straight from my graph. I know that a lower temperature will favour the exothermic reaction. I'll read through it again. And so therefore the forwards reaction producing COCl2 must be exothermic. And therefore I've got my response there. Technically, probably in here, I probably should have referenced to Le Chatelier's principle, saying that the lower temperature will favour the exothermic to partially oppose the lower temperature. However, this question doesn't specifically say I need to reference Le Chatelier's principle. So I just didn't, or I simply just forgot to do it. But it didn't state it, so Otherwise, if it did say reference Le Chatelier's principle, I would certainly put in partially oppose the change in my response. Question C, a third vessel is filled with the same amount of carbon monoxide and chlorine at T2, but also contains an appropriate catalyst for the reaction. Draw on the graph to show how the rate of phosgene production would differ from the first two vessels. So what we're doing T2, so therefore it's this one here, but we've got a catalyst. What does a catalyst do? So we'll find it here, catalyst. Catalyst is going to increase rate even more. So therefore, what's going to happen is it's going to be producing more. A catalyst, however, doesn't affect yield, so it will produce the same amount of phosgene, just at a faster rate. To make that easier, I'm going to draw my line back, but I'm going to cover it, sorry, I'm doing this badly, down here, and then I'm going to go like that. So therefore, this would suggest that I'm producing it the same amount, but I'm producing it quicker because my graph here is steeper. And that's my response for this, because a catalyst will increase the rate of reaction, so therefore my initial rate of reaction should be much steeper. That's part C. Let's have a look at part D over the page. Explain with reference to collision theory and a diagram of the Maxwell Boltzmann distribution how the addition of a catalyst affects the rate of reaction. That's the question right there, you can't see it. Anyway, let's have a look at it. Let's start off with the Maxwell Boltzmann distribution. What is that? I have got number of particles on my y-axis here, and then I've got my energy on my x-axis. I'll have a distribution of particles like this, and then I'll have at some point, I'll have activation energy. So therefore, these are the particles that can collide. What I'm then going to do is show what an addition of a catalyst does in my Maxwell Boltzmann distribution. A catalyst will lower activation energy. So I'm going to put another one here. I'm going to say that's going to be EA2. So therefore, I've got my EA1 without a catalyst, my EA2 with a catalyst. What this suggests is that with the catalyst, I have a greater proportion of particles with the required activation energy. So I have a greater proportion of successful collisions. So therefore, let's try and respond to that in words. Okay, so adding a catalyst will decrease my activation energy. This means a greater proportion of particles have the required activation energy. This is where buzzwords come into it. Greater proportion of particles have the required activation energy. So therefore, I have a greater proportion of successful collisions. So therefore, greater proportion, decreased activation energy, greater proportion of successful collisions, which is our buzzword for a catalyst. Remembering the fact that it's not just the greater frequency of successful collisions, it's a greater proportion of collisions which are successful in this. Last question here. Explain why most catalysts used on an industrial scale are often porous or meshes. What does porous mean and mesh? They mean they have holes in them. What that does is increase surface area. Porous / mesh catalysts will have a larger surface area, thus also increase / improve the rate of reaction. And again, linking the porous and mesh nature to the surface area. Technically, I could go down the path of saying, therefore, we have a greater frequency of successful collisions. However, this doesn't say refer to collision theory. With that, not a bad idea to do that, but in the interest of time, this is getting on to 9 minutes, 40 seconds already. I'm going to not do that. But please, if you feel free, if you notice the fact that you're talking about surface area and rates of reaction, try and add collision theory where you can. And that's the answer to question, what was that? 3, done.